Okay, so we've wrapped up weeks 1, 2, and 3. Remember, 1 was just kind of a backyard accounting of various energies in the house. Week 2 was getting some of the financial functions down, coding them by hand. And then week 3, we used the built-in functions. And like the 2 new functions we learned were net present value, where you're adding up multiple annuities, and then the if statement. You're just comparing 2 options. And that if statement is made, that choice is sort of made all the time. Just like in the little economics video we saw, it's the same, oh, do I ride my bike or take the bus? Do I eat breakfast or skip it? Do I, what would do I wear the heels or the boots today? And every one of them has some kind of economic consequence. And I think what we're starting to see now, and it's the same thing with which energy technology a country decides to go for. Just before coming to lecture today, I watched a interview where Neil deGrasse Tyson was interviewing Michio Kaku. So deGrasse Tyson is the astrophysicist out of New York, and Michio Kaku is the nuclear physicist who built a particle accelerator in his garage at the age of 13. And he's on I think they're both in New York now. I think Kaku's on the physics faculty at Columbia, but Michio's ancestors were Japanese. They've been in the U.S. for 100 years, and he was talking about all of the dangers that still exist at Fukushima. So they're still just pumping water on that core like crazy to keep it cool. And the example he used is that you're driving along in your car and your brakes go out. You're trying to stop it, but you can't because you got no brakes. Well, the accelerator is stuck to the floor too, and so your radiator starts to overheat. Your radiator overheats and your engine's about to blow, right? So what do? You drive off the road into the river. Just cool the whole thing off. Well, at least I can steer. I'll just steer. So right now it sounds like, and this was published a month or 2 ago in December, and apparently there were 800 people working there. Now there are 50, and they're still working in this radioactive environment. Like, these people are just kind of, well, I don't know. It's either that or she's gonna blow again, because there's this hot core of nuclear.
Thanks for the people sacrificing
their
lives.
Yeah, and Kaku said that there's these folks are down there just saying we suffer quietly is their philosophy. But the point, the weird point, and this is true in a lot of different cases, is that they're using, I don't know exactly where the electricity is coming from, but they're pumping water into the core, and and you don't just pump it in once.
Right.
You got to circulate it because you pump it in once, it just gets hot, and now everything's the same temperature. Right. So the weird irony about the nuclear power plant is now we're like, spending energy. Where the energy's coming from? It's probably not a bunch of solar panels sitting out there. Just guessing. We're spending energy to keep additional disaster from happening. A lot of energy. Same thing is true with the Berkeley pit. So at the pit, and I was talking with someone. Apparently there are pumps running, and it could be that these pumps are actually running at 43 megawatts. So 43 megawatts would be enough to.
Is that per day?
No, it's like 43 megawatts. There's a 43 megawatt light bulb on.
Oh my God.
It's just on. It's a 43 megawatt pump. It's just running. It's a. Well, let's see. It's maybe 5. It's 2%, 2.5% of coal strip. is basically what it comes down to. Is
Oh,
and I think all of that is just to pump the water out.
well, what they're doing is they're pumping it through the other underground lines.
Exactly. Yeah, so it's not,
Constantly moving it, that's
yeah,
all they're doing.
yeah.
Not
yeah.
realizing the bigger problems they're causing.
Right, yeah, so I've got a couple little ideas on how to solve the Berkeley Pit problem
Pull those
too.
butte out.
No, I think it'd be fun just to boil the water off with solar thermal. So you just start boiling it without heat, just the heat just comes from the sun, right? So we've done this with Fresnel lenses, made steam, and then all that water runs up on that northern face that faces the south, and then just start vertical farming right there with all that great water. And I think just let the core of the pit stay solid,
You'd have to.
and just use it for just use it as a giant dump. Just use it as a solid dump. Okay, here comes your lead, here comes your chromium, here comes your heavy metals. Just yeah. Okay, that's my 2 cents on the Berkeley Pit.
My Berkeley Pit is nasty.
Yeah. Well, and there's so many people, like with the geese dying, and oh. I'm gonna make one quick little edit while we're in here.
Yeah, he's awful early. This place is quiet today.
Yes, I'm just gonna take this guy. Been trying to slowly kind of clean up the website a little bit, just make it a little bit tidier. All right, so why use 2 lines when you can get it all done in one? Get rid of the hypertext. Bingo. Save changes.
Maybe.
Give me a sec. Okay, so week 4, intro to electricity utility commercial rates, energy and demand. So now what we're going to look at is the cost of just electricity. So let's take a peek into week 4. This is kind of key. The generation, so this is true, well, this is true whether or not you have storage. Right now there is virtually no storage in Montana. The Gordon Butte project is going to change that. We'll have pump storage. And so the load can be, gosh, the computer that's turned on right now, the light bulb, the car charging, what have you, any electrical load. And the generation is sitting out there on multiple fronts. You have dams, nuclear power plants, wind turbines, solar farms, coal-fired power plants, gas plants, the works. And if depending on the load versus the generation rate, this can mess with the frequency. One of the coolest things I ever saw, we were there in Butte, and we were in the control room for Northwestern Energy, and there was a voltage and a frequency plot. And so the whole point is you don't want the voltage to get too high, don't want the voltage to get too low, don't want the frequency to get too high, don't want the frequency to get too low. So if you're pulling faster than the grid can generate, you're going to drop the voltage and you're going to expand the frequency. If not, then the voltage goes up and the frequency tends to rise. The whole point of that control room is to keep those two in sync. It's a trip. Okay. So, the introduction of unscheduled and non-dispatchable, I mean, you don't turn it on or off. You're like, hey, turn on, all right, here comes the sun, here comes the wind. It made the balancing job more challenging. Okay, so here's the whole point. Energy storage offers a way to buffer or dampen the difference between generation and load. That is the whole point. And we're going to see generation coming online like gangbusters. It just has to in the near future. Through the pump storage, through batteries, who knows, maybe someone's going to do a flywheel deal. Compressed air, we're going to see compressed air in this course too. So, yeah. So this week we're going to look at the cost of energy in kilowatt hours as well as the demand fee. So you're going to get charged per kilowatt hour. Residentially, you're not going to see this, but if all of a sudden you're like, hey, I need 10 kilowatts, you're going to pay for that. You're going to pay a premium for that 10 kilowatts. That's what the demand fee is. The other point is, if you hit that once in 15 minutes, cha-ching. Okay. So let's take a look. Take a look at these. Demand factor, use factor, two different load factors. And then we're also going to do power factor, which is fun. So load factor is just what percentage of full load where it's running. Very simply, 100 horsepower with a load factor of 85% is 85 HP. Very simple. Full amp loads is just how many amps can be pumped through the system. And you'll have to remember our amps times volts to get power. And here's an example. So here's your horsepower. It can be run at either 230 or 460 volts, three-phase. At 230 volts, it's going to be running 175 amps. At 460, it's going to be running 87. Okay, in terms of the load factor, so your total kilowatt hours divided by the demand times the hours. That's how the load factor is calculated by the utility, so we'll have to just remember that. So there's a lot of detail in here. So what we're looking at is actually the kilowatts used during a demand period. Because obviously you're consuming kilowatt hours, but they divide that by the time, and then you end up with kilowatts. Okay. Standard use factor would be this many, 8,760 hours in a year. The use factor can be some fraction if you don't use it. So the load factor is like right now, and the use factor is over a year.
Okay.
Okay. So problem one, annual operating cost. So here's your motor, Monday to Friday, all year long. Et cetera, et cetera. So it's just like, how much does it cost to run that motor?
Okay.
Problem two. This problem gets a little bit tricky. So, but look at resources 4. It'll tell you what the rates are for running them. And there will be some times where, oh my gosh, I went over, I'm going to have to pay more. That's the whole point.
Okay.
Yeah, so the first one's pretty simple. The second one's like, oh, now I have to put in the demand factor. Yeah.
Folks that can discuss it, do we discuss these things?
If you want to, I mean, the discussion's really just there, the discussion's really just there to work through the problems as a team, as a class, as a group. But, everything's here to use, no real tricks. It just gets a little more complicated because we're talking energy versus power, and this is good, it's real, so. Have fun,
Oh, yeah.
and don't forget to take these 2 quizzes.
I won't.
Yeah.